Hello and welcome to this video tutorial. Today we're going to look at the notes for Unit 4, Momentum and Impulse. In this video, we're going to be not only defining the concept of momentum, but how momentum relates to forces applied, how momentum relates to Newton's laws. We'll discuss not only momentum, but changing momentum and also conserving momentum, keeping the total amount of momentum constant. And we'll do that by applying it in the form of studying two masses that either collide or separate after. So you could have two masses that collide, or you could have one mass that starts as one and sort of explodes into pieces. One piece goes one way, one piece goes the other way. Alrighty, remember to pause or rewind the video and let's get started. Momentum, part one. Well, we can define momentum as the quantity of motion, but you can also think about it as really how hard it is to stop an object. Inertia relates to how hard it is to change the speed of an object. So you can see how they're related. If momentum is how hard it is to stop an object, right? Inertia is how hard it is to change the speed of an object, right? You can see that we're dealing with mass. Mass is a part of momentum. Now, inertia is not equal to mass, but it's very much related to the mass of an object. More massive objects are harder to change their speed because more massive objects have a greater inertia. But more massive objects also have more momentum, right? Because again, mass relates to inertia, inertia relates to the difficulty in changing speed of an object, and momentum relates in the difficulty of stopping an object once it's in motion. So definitely mass is a contributor to momentum. So let's take a look at this table here and let's kind of describe what's going on. So a ping pong ball moving at 20 meters per second. Well, its inertia would be really, really tiny because, I mean, we're talking about a very small mass. So it would be very easy to change the, 20 meters per second is about 45 miles per hour. It's a little between 40 and 45 miles per hour. So even a ping pong going that fast, I mean, it's still a very low amount of inertia because of its small mass. And because of its small mass, it also has a very tiny momentum. Okay. Now, how about a train going at about 20 meters per second? Well, that is a very large, that's a huge inertia. You would have a hard time stopping that train, but consequently, you would also have, right, a large amount of momentum going on. A train at rest. Well, a train at rest also has a large amount of inertia. Now, think about it. Okay, inertia is all about the resistance to a change in motion. So if a train's at rest, it takes a lot to get it going. Therefore, it has a huge amount of inertia, no matter if it's moving or not. It just takes a lot to get it going or to change its speed, and that's because of its enormous mass. However, the momentum would be tiny. In fact, you could even go so far as to say a train at rest would have zero momentum, right? A bullet going at 50 or 500 meters per second. Well, the inertia of that bullet is going to be tiny simply because of its mass. Its mass is tiny, right? But its momentum is going to be medium to huge. Okay, now think about that, right? The momentum of a bullet going 500 meters per second is over 1,000 miles per hour, okay? That it's going to be hard to stop that. It's going to pass through a lot of things. So I would venture to say it's probably on the larger, the huge side of momentum. What do we see here? Momentum completely depends on mass and velocity. In fact, we can go further to say that momentum, the equation for it is momentum is equal to mass times velocity. So let's break this down. P stands for momentum, the unit of which is kilograms times meters per second. M is still mass in kilograms, and V is still velocity in meters per second. So you can see that the unit for momentum is a combined unit of kilograms times meters per second. Okay, in this example, what is the momentum of a 0.01 kilogram bullet traveling at 500 meters per second west? Well, P equals mv. We're going to plug in 0.01 kilograms for the mass times 500 meters per second for the velocity. Okay, now if you multiply 0.01 times 500, you'll get 5, right? Now the unit would be 5 kilograms meters per second. Now, if the bullet is traveling west, that means the momentum is west. Okay, momentum is a vector quantity and thus has a direction just like velocity does. Part 2, conservation of momentum. Well, we can define it as total momentum remaining the same. Now, it's only remaining the same, of course, in the absence of an outside force. Okay, so in other words, if something's moving, right? If something's moving and there's no friction acting on it, well, then it's going to stay moving at the same constant speed. And if it has the same constant speed, same mass, it's going to have this same momentum. Momentum's going to stay the same. But we also find that momentum stays the same even when objects collide with each other. Because when objects collide, they apply forces on each other, but there's no external force acting on the system. When an object separates into two pieces or, explodes into two pieces, same idea. You have essentially equal and opposite momenta because you started with 0 momentum. Now, more on that one a little bit later. Our problem-solving strategy is going to look like this. Number 1, sketch something before and after. It'll really help you sort out the details and help you organize the problem. 2, find P, that's the momentum. Find the momentum before and after collision. Okay, 3, P total before the collision equals P total after the collision. And finally, solve for whatever unknown you're looking for. Let's go ahead and try to apply this in example number 1. So part C, example number 1. A 200 kilogram car moving at 30 meters per second hits a stationary car of 300 kilograms. The 300 kilogram car moves forward at 25 meters per second. What is the velocity of the 200 kilogram car? Let's again sketch this out into what are called before and after pictures. So before, and I'm not going to draw the car as a car. I'm just going to draw it as a block. So we have a 200 kilogram car, and it's moving with a speed of 30 meters per second. Okay, and it's going to strike a 300 kilogram car initially at rest. Okay, and that's the before. We'll do the math in a minute. We'll do the work, but let's just set it up. So afterwards, the 300 kilogram car, the one that was at rest, moves forward. So this car, the 300 kilogram car, moves forward with a velocity of 25 meters per second. Question is, what is the velocity of the first car? That's what we're looking for. So we're looking for that velocity after collision. So again, taking the time to really draw a picture and sketch it out is really going to give you a strong indication of what the variables are, how to organize it and such. So let's figure this out. The momentum, I'm going to call this mass 1. We're going to call this mass 2. So P1 is going to be M1 times V1. So P1 initial, because it's before collision, is equal to 200 times 30. So P1 initial is equal to 6,000 kilograms meters per second. Now, P2 initial equals 0 because you're at rest, right? So what that means is P initial equals 6,000 kilograms, times meters per second. So it's basically I'm adding 6,000 plus 0. Okay, that's my total initial momentum. All right, so now we go to the backside. Okay, my total final momentum. Well, Total initial momentum is supposed to equal total final momentum. So that's supposed to be 6,000. Okay, more on that in a minute. All right, but let's figure out some things. Okay, P1 final is going to be 200 times V. We're looking for V. Okay, now over here we have P2 final, which is going to be 300 times 25. So P2 final is going to be 7,500 kilograms meters per second. Okay, so now what you can see here is that in order for this, think about this for a second. This plus this momentum here, P1 final. In order for those to add up to this clearly has to be negative. Okay, so now what would it be? Well, you can see that if I subtract the two, this would have to be a total of negative 1,500 kilograms meters per second, right? Because if you add those up, what's negative 1,500 plus 7,500? Well, it's 6,000. So now I take this, okay, and I have 200 times V equals negative 1,500. Go ahead and solve it for V. Divide out the 200. And V, right, is equal to negative 1,500 over 200, which is negative 7.5 meters per second. Okay, so what's up with the negative? The negative means that after collision, this mass is rebounding back to the left. Okay, this one goes to the right. The 200 kilogram one rebounds back to the left. So that's the indication of that negative sign right there. So again, conservation of momentum is something that it's a bunch of mass times velocity calculations, but we have to make sure that the total momentum before gets set equal to the total momentum after as we're doing the problem. Okay, question 2. A 400 kilogram car traveling east at 15 meters per second. Okay, let's go ahead and draw that. So this is before. So we have a 400 kilogram car is moving at 15 meters per second. And it collides completely inelastically. Now, when we see this phrase right here, what that basically means is the two masses stick together. That means we have to add their masses after collision, okay? More on that in a minute. So the 600 kilogram car, it's a bigger car, is moving west at 8. Okay, now if it's moving west, I have to make that negative 8 because this one is already positive. Okay, that's before. Now after, what happens is the two masses, they stick together. 400 and 600, so they get a total mass of 1,000 kilograms. Okay, so that's what's going on. And if you think about it, there's more momentum coming from this one than there is this one, okay? And you can figure it out, okay? P1 initial is M1 V1, okay? P2 initial is M2 V2. It's just mass times velocities, okay? So P1 initial is gonna be 400 times 15, which is 6,000 kilograms meters per second. Whereas P2 initial is going to be 600 times negative 8, which is negative 4,800 kilograms meters per second. So the total P initial, right, is the sum of those two. Add them up. Right? Add them up. That's the total. The total would be 1,200. right? If we subtract 6,048, we get an initial momentum of 1,200 kilograms meters per second. Well, guess what? If momentum is supposed to be conserved, and it is, that means total momentum before equals total momentum after, and that's also got to be 1,200 kilograms meters per second. Okay, but here's what we know. We know that the mass is now combined. So we can take that information, P final equals, I'm going to call it big M because it's now a combined mass, times velocity. And we're solving for the velocity. So go ahead and divide away the big M. And we get that the velocity is equal to the final momentum, which is the same as the initial 1,200 kilograms meters per second. And we're going to divide that by the total mass, which is we get when we add those together. 600 plus 400 is 1,000 kilograms. And you'll notice the unit of kilograms cancels, by the way. Dividing those two, you get 1.2 meters per second. Now, since the answer is positive, that tells us, that tells us that the combined masses move this way. Now, they're moving that way, but since it is such a large mass, right, it was going 15 compared to -8 the other way, it's moving at a much slower speed because of that combined mass. Number 3. A 2-kilogram rifle fires a .05 kilogram bullet at a velocity of 500 meters per second. What is the recoil speed of the rifle? Okay. So before, here's kind of what you have. You have, okay, rifle with bullet inside, okay? And here's what I'm going to tell you. I'm going to say mass 1 is the bullet. Mass 2 is the rifle. Okay. Now, what does this mean? P1 initial, that's the bullet, is 0. P2 initial, that's the gun, is 0. That means P initial is 0. Okay, that's 0. But here's the thing. P total, so after P final should also be 0, right? Okay, so now what do we have going on here? Well, when the gun fires, the bullet flies this way. The gun recoils backwards that way. Okay, now we're told that the bullet flies with a velocity of 5. And actually, let me, I'm going to kind of draw this the other way just to kind of, there we go. Sorry about that. Okay, so the gun, the rifle, is going to recoil backwards. Okay, and we're looking for that. That's the unknown. It's the recoil speed of the rifle. The bullet, on the other hand, okay, has a momentum. So M1, V1, right, is going to be P1. And this is P1 final, because this is the momentum of the bullet after collision. Okay, so P1 final is going to be, what, 0.05 is the mass times the velocity of 500 meters per second. Multiply those and we get 25. 25 kilograms meters per second is the momentum before. So now that has to be equal and opposite. We have to have equal and opposite final momenta. Okay, in other words, for this to be 0, okay, what that means, if you think about it, that means 0 equals P1 final plus P2 final. That means these two have to be equal and opposite to each other. P1 final is equal and opposite to P2 final. Okay, so if we're looking for P2 final, right, is equal to mass times velocity, and P2 final is going to be equal and opposite to P1 final. solving for velocity, right? P2 final divided by the mass. P2 final would be negative 25, because remember, it's the same magnitude, but it's opposite in direction, kilograms meters per second, over the rifle's mass of 2 kilograms, right? You can see the recoil speed of the rifle is going to be much slower at about negative 12.5 meters per second. Still fast enough that you wouldn't stick your eye right behind the eyepiece, okay, but not definitely not as fast as the bullet. Okay, again, what's the indication of the negative? What does that mean? The rifle is moving opposite the direction of the bullet. Bullet's moving right, rifle's moving left. Okay, so now a couple things to note. An elastic collision is one in which there is no loss in kinetic energy. So in other words, we not only have conservation of momentum, like we do in every collision, but we also have conservation of kinetic energy as well. So kinetic energy remains constant. Now, visually, you could see this as two objects that kind of bounce off each other without sticking. That's kind of the idea, is they just don't stick together. In inelastic collision, by contrast, you're going to have a loss in kinetic energy. Okay, so this one is only conservation of momentum. Okay, conservation of momentum, and there's a loss in kinetic energy. Kinetic energy is not conserved, okay? And visually, you can see this as two objects that are sticking together and their masses combine, kind of like we saw in this example here. That's an inelastic collision. Part 3. Impulse. Well, we could define an impulse as a change in momentum, and the variable for impulse is going to be a j. Now, the equation we can use for it is, well, it's a change in momentum, delta p. But we could rearrange this a couple different ways, and we could write this as change in mv. But that might not be the best way to write it. So what we're going to do is write, because what's really changing, it's not the mass. The mass doesn't change. It's the velocity that changes. So it's mass times a change in velocity. Or how about this? We could write it as simply mv final minus mv initial. Okay, so that's one way we can calculate the impulse. Now, impulse is also, in order to change the momentum, there must be a net force applied. So in other words, another way we could figure this out, your change in momentum, there has to be a net force applied. And it's applied over a time interval, delta t. So you have two equations here. Impulse equals a change in momentum, mv final minus mv initial, and the impulse equals force times time. So you have two different equations that you're working with for impulse. Now, sometimes you can set the equations equal to each other and just have force times change in momentum equals mv final minus mv initial. Okay. Now, one thing to think about conceptually when it comes to impulse, especially with the force times time here, if you're changing the momentum, if the momentum change is the same, then the more time you apply, the less force there is. So for instance, if we had, let's say, something that was falling to the ground, okay, and it hits the ground, splat, like a watermelon. Watermelon crashes, falls on the ground. Well, its momentum is going to come to zero. Its final momentum comes to zero. Okay, so the change in momentum is going to be whatever it had before, right? But then it comes to zero. So it has a change in momentum. But then let's say we take watermelon number 2 and we drop it into some water. That watermelon is going to take time to come to rest. So it still comes to rest, but it does so delta t seconds later, more time. More time meaning less force. Less time, more force. Okay, so the equation J equals F delta T, think of it like this. If the time during the impact is greater, if there's more time, we'll experience less force. Okay, right? Consequently, if we have less time during an impact, then we're going to experience more force. So there's a trade-off between force and time conceptually. All right, let's take a look at example number 1 in part C. So it says a 20 kilogram cart is moving at 10 meters per second to the east, collides and sticks with a 30 kilogram cart moving 8 meters per second to the west. So again, draw your before and after. So before, I have a 20 kilogram cart, and it's moving 10 meters per second east. East would be to the right. And it's going to collide and stick with a 30 kilogram cart. But the 30 kilogram cart is moving 8, in which case I'm going to call it negative 8 meters per second to the west. Okay, what is the speed of the carts after collision? Now, if they stick, here's what you get after. You get a 20 plus 30 or 50 kilogram mass. Okay, the masses stick together. So we want to figure out the speed after collision. Okay, then we want to figure out the impulse on each cart. All right, let's take a second, one at a time. So part A, here's how we're going to deal with part A. First, let's figure out the momentum before and after. So P1 initial is going to be M1 V1. That's going to be 20 times 10 or 200 kilograms meters per second. Okay, P2 initial is going to be M2 V2, right? And that's going to be 30 times negative 8, which would be negative 240 kilograms meters per second. So P initial, the initial momentum, right, is the sum of these two, or negative 40. Negative 40 kilograms meters per second. So part A would be finding the speed after the carts. So the final momentum is also negative 40 kilograms meters per second. Okay, and the final momentum is going to be equal to the sum of those two masses times the velocity. Solve for the velocity, and it's P final over the sum of the masses. So negative 40 kilograms meters per second over the sum of these two masses, which adds up to 50. Okay, V final for these would be negative 0.8 meters per second. Okay, so part A is a conservation of momentum problem in which we have what's called an inelastic collision. So let me just kind of separate this a little bit. Part B is looking for the impulse on the 20 kilogram cart. So the impulse is equal to essentially mv final minus mv initial. Okay, what is the 20 kilogram cart doing? Well, we have a mass, 20. Now V final is 0.8. So negative 0.8 minus, okay, now we're going to go 20 again, times V initial. V initial was 10. Okay, so 20 times 0.8. So we have negative 16 minus 200, and we get an impulse of negative 216 kilograms meters per second. Oh, one more thing. The unit for impulse is the same as momentum. right? Kilograms meters per second. But if you look at it here, it's also equal to a Newton second. Newton second is the other unit for impulse. Okay, so we have part B. We've got our impulse on the 20 kilogram cart. Now part C is very, very similar. Okay, the impulse on the 30 kilogram cart, again, is going to MV final minus MV initial. And sometimes it helps. Maybe write M2V2, right? Final and initial, because that might help keep it straight as far as which mass you're talking about. This being mass 1, right? This being mass 2. So try to keep yourself organized. So we have a 30 kilogram cart. Okay, its final velocity, negative 0.8, just like the other one, minus, again, 30 times its initial velocity, which was negative 8. Okay, so when we go 30 times 0.8, we get negative 24. Minus a minus is a plus. 30 times 8 is 240. Right? Add those together and we get positive 216 kilograms meters per second. Let's think about that. How does that make sense? The total momentum, P total, is equal to negative 216 plus 216, right? Equals 0. The change in momentum. This is the total change in momentum. The total change in momentum is 0, which means what? Momentum is conserved. It's kept constant. And so that's what you're going to see, ladies and gentlemen, when you do conservation momentum problems. We let the total momentum stay the same, but if we break it apart into individual masses, what it means is the impulses on these objects are equal and opposite to each other because the forces they apply on each other are equal and opposite. So we have equal and opposite impulses when we calculate them. Okay, we didn't do part D. Part 4, rather. We'll call it part D. I don't know why I didn't see that. It's labeled, A, B, C, and D. So part D, we'll do that down here. It says, if the collision took 0.02 seconds, what was the force on the 20 kilogram cart? Well, it also equals force times delta t. So solve for delta t, and it's the impulse divided by the change in time. The impulse on the 20 kilogram cart was negative 216. This time I'm going to write the unit as Newton seconds. You'll see why in a minute. Remember, Newton second or kilograms meters per second. Okay. And by the way, here's why. Here's why that is. Let me show you real quick. Okay, force is equal to mass times acceleration. That means 1 Newton is equal to a kilogram times a meter per second squared. That's what a Newton is equal to. So if we have a Newton second, that is equal to a kilogram meter per second squared, that's the Newton, times seconds. Well, this cancels with this, and what are you left with? Kilograms meters per second. That's why this unit is equivalent to this unit. Just thought I would throw that in there real quick. Okay, go ahead and divide that by the 0.2 seconds. You can see the seconds cancels, and we end up with a force, let's see, 216 divided by 0.2, a negative 1,080 newtons. Okay, negative because it's the force applied back on the first mass. The force applied back on the first mass is headed to the left in the direction of the first mass. Therefore, it's negative. Right. Example 2. A 0.2 kilogram egg is thrown at a wall with a velocity of 10 meters per second and comes to stop in 0.05 seconds. A second egg is thrown at a pillow and comes to rest in 0.5 seconds, so greater time. Compare the impulses, momentums, that's pretty bad right there. That should be momenta. Momenta is plural for momentum. And forces for the two eggs. Okay, let's go ahead and break this down. So start with the wall. Okay, so I'm going to zoom in on this. Okay, what do we have here? We've got the mass, okay, and it's a 0.2 kilogram egg. The velocity is 10. The initial velocity is 10 meters per second. The final velocity is 0 because it comes to rest. And the time it takes to do this is 0.05 seconds. Okay, so what do we have? We have delta P, the change in momentum. Okay, so J equals mv final minus mv initial. Okay, let's figure out the impulses right here for the wall. Okay, so we've got the 0.2 kilograms times v final, which is 0, minus 0.2 kilograms times v initial, which was 10. And we have 0 minus 2, or negative 2 kilograms meters per second. Okay, so the impulse, right, is negative 2. Now, the force, we got to take that same impulse, but this time set it equal to F delta T. Okay, solve for F, and F equals the impulse divided by your delta T. So negative 2, I'm going to write the unit a little bit differently, Newton seconds this time, divided by 0.05 seconds. You can see that cancels. And the force would be 40, negative 40 newtons applied back on the egg. Hence, it's a pretty strong force, and the egg would break if it hits the wall. Okay, let's take a look at the pillow. So for the pillow, we have a same mass, same egg. The initial velocity is still 10. The final velocity is still 0, still comes to rest. The difference is the time it takes is much longer. Okay, greater time. So if we look at the impulse here, the change in momentum, mv final minus mv initial, we have a mass of 0.2 times 0 minus the mass of 0.2 times 10. And if we compare, again, we get 0 minus 2, which is negative 2. So if you see, ladies and gentlemen, the impulse, when you have the same initial speed given to two different situations, okay, they're going to have the same change in momentum because they're going to have the same initial speed, same final speed, right, and same mass. Therefore, they're going to have the same change in momentum, same impulse. But because the time is much greater here, force equals impulse divided by delta T when you solve it. This time it's negative 2 Newton seconds over a half a second, in which case we get negative 4 newtons. So there's 10 times less the force when an egg hits a pillow than when an egg hits a wall. Therefore, what happens? The pillow increases the time during the collision and this decreases the force on the egg. Okay, in our final section, we're going to look at how we can apply this graphically. Okay, so if we're given a force time graph, well, let's think about this. Area would be multiplying length times width. In other words, force times time. Now, what do you get when you multiply force times time? Well, force times time is impulse. Therefore, impulse, right, or a change in momentum is an impulse, right, delta P, that is going to be the area under the curve. So this is what all of that is going to equal. Okay, so the force acting on a 20 kilogram mass is shown in the graph below. What will be the change in speed of the mass? Well, to figure out the change in speed, we do need to figure out the change in momentum, okay? Because impulse is equal to a change in momentum. The impulse you're going to get from the area. And we have mass times a change in velocity, and you're looking for a change in velocity. So let's go ahead and figure this out. We'll divide it by the mass, and a change in velocity would be equal to the impulse divided by the mass. So the impulse is going to be this shaded area right there. Let's figure that out. The impulse would be the area, which is that of a triangle. 1/2 times the base, which is 5, times the height, which is 30. Which would be 75 Newton meters, or Newton seconds, or kilograms, meters per second squared, whichever way you want to look at it. Meters per second, sorry, not meters per second squared. So the change in velocity, right, would be the impulse divided by the mass, or 75 kilograms meters per second, divided by the mass of 20 kilograms. You can see the kilograms cancels there. And the change in velocity would be about, what, 3.75 meters per second. So we can get information about a collision, right, with a force versus time graph as well. Okay. That, ladies and gentlemen, concludes the notes for momentum, impulse, and conservation of momentum. I hope you found this useful to become familiarized with the concepts in Unit 4. Again, please remember to pause or rewind the video as you need to.